Hi, in this video we will have a look at how condensation polymerization occurs, and in particular how polyesters are formed. We will also look at some of the uses and properties of polyester. Condensation polymers are just like any other polymer. That is, they are giant molecules that are formed when lots of small molecules called monomers link or add together. Now, the monomers which are used in condensation polymerization have reactive functional groups present on each end of the monomer molecule. For example, you may recall that carboxylic acid molecules all contain the carboxyl functional group, COOH. For example, two common carboxylic acids that you are likely to have met are ethanoic acid and propanoic acid, which are both shown, and the reactive carboxyl functional group present in each of these molecules is highlighted. Well, another homologous series of carboxylic acids is called the dicarboxylic acids, and these molecules have the carboxyl functional group present on both ends of the molecule. So, for example, the first member of this homologous series is ethane dioic acid, and by simply adding a CH2 group to this molecule, we end up with the next member of this homologous series, propane dioic acid, and similarly, if we add another CH2 group, we end up with butane dioic acid. Now, when these dicarboxylic acid molecules react, it is only the carboxyl functional group that takes part in any reaction, and the rest or remainder of the molecule is unchanged. So we can simply draw these carboxylic acid molecules as shown. Now, recall that alcohols all contain the hydroxyl functional group, that is, an OH group bonded directly to a carbon atom. 3D models for three common alcohols, methanol, ethanol and propanol, are shown, and you should be able to see that each molecule contains a hydroxyl functional group. If we draw out the displayed formula for these three alcohols, it might be easier for you to see that each molecule contains a hydroxyl functional group. Now, another homologous series which contains a hydroxyl functional group is called the diols. However, as the name suggests, these molecules contain two hydroxyl functional groups per molecule. For example, the displayed formula for the diol molecules, ethane diol and propane diol, are shown, and again you should be able to clearly see that each molecule contains two hydroxyl functional groups. We can simply show the structure of these diol molecules as shown. Here, the box represents the portion of the diol molecule which doesn't react, and the two reactive hydroxyl functional groups are drawn on the end of each box. Now, you may recall that esters are molecules formed in a condensation reaction between an alcohol and a carboxylic acid, and that a condensation reaction is one where small molecules react to form a larger molecule, and a small molecule such as water or even hydrogen chloride is released. For example, the alcohol ethanol will react with the carboxylic acid ethanoic acid to form the ester ethyl ethanoate and release a small molecule of water. Here, the OH group present in the carboxyl group on the carboxylic acid reacts with a hydrogen atom on the hydroxyl group present in the alcohol molecule to form a molecule of water, while the remainder of the acid and alcohol molecules now join together to form the new ester bond, which is clearly highlighted. So what would happen if, instead of using a carboxylic acid and an alcohol to form an ester, we used a diol and a dicarboxylic acid? Well, this time the hydroxyl group on the dicarboxylic acid will react with a hydrogen atom from the hydroxyl functional group on the diol to form the ester linkage, and at the same time a small molecule of water will be released exactly as before. However, if you look carefully, you will see that the ester molecule formed still contains a reactive carboxyl functional group on one end and a reactive hydroxyl group on the other end of the ester molecule. This means that this ester molecule can now react with another dicarboxylic acid and another diol molecule to form new ester bonds. That is, we will form a polymer with lots of ester groups. That is, it will form a polyester. We have already seen how a diacid monomer can react with a diol monomer to form a larger molecule which contains an ester linkage, and that this condensation reaction also released a small molecule of water. However, to build up a polymer containing many ester linkages, that is a polyester, the reactive end groups present need to react with more diacid and diol monomers. This will result in the loss of an OH group from the carboxyl group on the diacid, and also the loss of a hydrogen from the hydroxyl group on the diol, and this will result in the formation of another molecule of water. The removal of the OH group and the hydrogen will also give the structure for the repeat unit for the polyester, and we can write an equation to show this condensation reaction as shown. Here, N is simply the number of diacid and diol monomers which react, and recall that the repeating unit is usually shown in brackets. Let's finish this video by looking at some of the common uses for polyester. If you had never heard of polyester before, then a quick look at the label on your clothes will probably reveal that polyester is part of the material your clothes are made from. The polymer polyester can be made into fibres, which are then spun and woven into many types of materials. Polyester is an inexpensive, strong, durable polymer which is resistant to normal wear and tear. It is moisture resistant and stain resistant, which makes it ideal for use in many types of clothing such as trousers, shirts, blouses, skirts, and in many types of athletic wear. However, polyester is not breathable, so it is often mixed with other fabrics such as cotton to improve the comfort and wearability of garments. However, its uses are not limited to clothing. Shoes, tents, sports bags, safety belts, and even carpets are all commonly made from polyester, while many soft drink bottles are made from a polymer called PET, which is a form of polyester. However, it's not all good news for polyesters. Being a synthetic polymer, most polyesters are very slow to decompose totally, taking anything from 20 years to hundreds of years to break down in the environment. Polyester microfibers and microplastics can also end up in many waterways, seas and oceans, where they can harm many forms of marine life. And finally, polyester is not a sustainable material, since the main material used to manufacture polyesters are obtained from crude oil. Hi, thanks for taking the time to visit this channel. If you need more help and information, then why not visit the website that accompanies these videos? The links are in the description below. If you found this video helpful, then please don't forget to like and subscribe. Thank you.